Uh, Respected speaker, other dignitaries, friends, ladies and gentlemen. Good afternoon, everybody, and a happy Teachers' Day. Now, I request all of you to please focus on the slides rather than my face because you see I'm wearing this cap on my head today because there is no hair inside, and please pardon me for that. I was wondering how to bring in some variety into today's introductory session, and unfortunately, here you have it. Let's leave that. Usually, we have 2 months of summer vacation in India and other places as well. But this time, it has been somewhere around 5.5 months since I went to school. Even though it is not a vacation, you have online classes and things. But even then, not being able to go to school, not being able to see your friends, not being able to see your teachers, and kind of like not being able to go out the way we used to is pretty tragic. But this definitely, things definitely ain't going the way we wanted it. But even then, whatever be the case, for the past 15 weeks, we here in UL Space Club have been busy and I believe are successful in bringing experienced speakers to interact with the public. We've witnessed 12 sessions from, excuse me, sir, there is a small glitch. Let me continue. We've had 12 sessions from experts, 3 from students, and one of which happens to be myself. We switched over to a national webinar series in English. We've had an exclusive Malayalam webinar. We've introduced UL Space Quiz along with our webinars. Moreover, we've even had grand functions on Moon Day and Kalam Memorial Day. In that sense, things are pretty good. Not pretty good, in fact, very good indeed. The participation from the students in our Q&A sessions and our quizzes have been very joyous to watch. And we are constantly working on how to make things better. Today, it is my honor to welcome our speaker, Shri Prasanna G, Head of Composite Pressure Vessel Design Division at Vikram Sarabhai Space Center, ISRO, Thiruvananthapuram. Hearty welcome to you, sir. We also have an experienced group of professionals from ISRO and top universities in and out of the country. It is my honor to welcome all of you. I would also like to welcome the Chief Patron and Mentor of UL Space Club and former Director of ISRO, Shri E.K. Kuti sir. I would also like to welcome the moderator of today's session, Shri U.K. Shajil sir, and the moderator of today's Q&A session, which is Master Shri Ram D. We also have Shri T. Damodaran sir representing UL Education and who is going to give the vote of thanks. Now, welcome to you, sir. But it is all incomplete without the participation, the participants of our sessions. And seeing you benefit from the sessions is what keeps us going. I happily welcome all of you to UL Space Club Webinar 16, Maths in Nature, Life, and of course, Space. Maths, probably not the most favored subjects by most students. But if you have a look around, in detail, you'll understand that everything at its deepest is mathematics. In fact, life itself is nothing but a series of calculations. Hence, we believe that today's session will be extremely beautiful. Before moving into further proceedings, let me take a few moments to announce the results of UL Space Quiz 15, Exoplanets and the Search for Habitable Worlds. You know that after every webinar session, we have a quiz competition over Google Forms called the UL Space Quiz. It is not mandatory. The participants can attend the questions based on what you've learned today and some other general knowledge on the topic of discussion. The top 3 will be selected based on their accuracy and the time of submission. The first prize winner will also receive a cash prize sponsored by Cinderby Nurture. You will receive the link to the quiz at the end of the session in the chat box. And most importantly, the link to attend the quiz will only be activated once the whole session of today's is concluded. And you have to submit your answers fast, and the submission has to be at least before 7 p.m. tonight. Now, here are the results of UL Space Quiz. Please wait a moment. Here are the results of UL Space Quest 15. As we usually do, let's go the conventional way, starting from number 3. The third spot is for Eldo Sam Verghese, and he's an 11th standard student from GVHSS Madapalli. Congratulations. The second prize is for Han Joseph Anup, and he's a 10th standard student at MGM Higher Secondary School, Manathavadi. Congratulations, Han. The first prize winner is Tushar Singh Amrelia, and he's a 10th standard student studying at St. Mary's Convent Senior Secondary School, Bhopal. Congratulations, Tushar. Congratulations to all winners and all participants, and best of luck to all of you for today's quiz as well. Now, moving into today's proceedings. After the talk, we will have a Q&A session, otherwise known as the question and answer session, which is moderated by Master Sriram D. The participants can ask your questions, but you are requested to post your questions firstly in the chat box. You can post your questions anytime, and they can be in either in English or Malayalam, but take care to type the questions in their respective alphabets, like type English questions in English alphabets, and if you want to ask Malayalam questions, please do type them in Malayalam alphabets. Avoid typing Malayalam questions using English alphabets the way we are used to during chatting. So the reason is that there might be a few problems in translation. So you can opt either way, that depending on how you want. The best questions will be articulated and will be asked to the speaker and our panel of experts. The session today will be followed by the 15th edition of UL Space Quiz, as I mentioned earlier, as well as the announcement of UL Space Club Webinar 17, going to be held the next Saturday, will also be given. Now, let me conclude by requesting all participants to do certain things. Firstly, to make sure your mics are muted and your cameras off during the talk. Also, take care not to present your screens. Like if you leave the meeting and if you have to rejoin at any instant, please take care to click only on join and never click present. Please do not try to present your screens, because if you try to present your screens, the presentation of the speaker will be lost. So since we have to avoid this situation, I have a recommendation, a tip for all of you. When our speaker Shri Prasanna presents his screen, make sure that you pin his presentation. It is very simple. You have two options on the top right corner called chats and people. So go to people and you will be able to see a person named, I think it will be Shri Prasanna. I think Prasanna presentation, depending on his name. I think Prasanna sir will tell you. I request you, Prasanna sir, please do tell them. Then there will be something called presentation in the bracket. So click on it and pin that presentation so that it won't be lost even if someone else tries to present as well. So that is it. Without further ado, let me invite Shri UK Shajil sir to introduce our speaker and to illustrate the redefined systems of our webinar as well. Over to you, Shajil sir.
Thank you, Bharat, and a warm welcome to all to this our day, the Teachers' Day. And we are so happy to be here on this day. And it is our 16th webinar. The UL Space Club, that's functioning under Uralingal Labour Contract Society for the past 5 years. And now we are active in this COVID era. And we are proudly, we can say, we are improving a lot in our programs. And that is reflected in our participation and in the enthusiasm that's shown by our participants. And today we have the talk on maths. As the Gauss says, Frederick Gauss says that the mathematics is the queen of science. We selected this topic because the maths controls everything. That's why we selected the topic that maths is everywhere. And in life, maths in nature, life, and of course in space. We have a person from VSSC, Vikram Sarabhai Space Center, Trivandrum. And the UL Space Club is getting a good support and nurturing attitude from this prestigious institution, VSSC. And that's because of our chief guest, chief mentor of this UL Space Club, E.K. Kutisar. And with this support, we got eminent person from this VSSC. Today we have Mr. G. Prasanna, Head Composite Pressure Vessel Design Division, VSSC. the VSSC, his office is not in Tumba, he is from Baturka. And as he's a mechanical engineer, now he is placed with mathematics. There are a lot of space works and engines and rocket parts are developed in his division. That's the composite pressure vessel division. And he is working on the heart of all these launch vehicles. And when we consider his journey of academic, we can say that I would quote a proverb here: allow your passion to become your purpose, and it will one day become your profession. That's the things. His pathway is not a natural and a usual one. He stopped his studied in 10th standard in Madras High School in Chennai, and after completing his 10th standard, he joined to diploma course, and after completing the diploma course, he joined for BTech, and he hasn't met the +1 and +2 mathematics. But he has a passion for this mathematics. He studied on it, and he made his success over it, and he became part of BSSC 20 years back. And he proved his excellence in contributing his application mathematics in all the designs he is now doing. And now he is able to visit a lot of countries with this mathematics, and he become a good engineer and a good scientist, and he is honored with Young Scientist Award by ISRO. And we heartily welcome the king of mathematics and the lover of mathematics, Shri G. Prasanna to our forum. And one more thing I want to add, he is a lover of technology also. He knows how to use mathematics in technology. He is not using the paper pen method to use this mathematics. He is using high-end technology to show his or express his ideas in mathematics, and I am sure that he will reflect these ideas in his wonderful presentation we are awaiting here. And today is the Teachers' Day, and I dedicate this session, the 60th session of this our webinar, to two teachers who already participated here. One is a national award winner from Trivandrum, that is Suresh sir, and one is our Unnikrishan sir. I invite the two beloved gurus of Kerala to this forum again one more, and I wish to dedicate this thing for these great teachers of India. And I dedicate all other teachers this forum and outside the forum, and I invite all the students and the veterans of ISROs and scientists and young persons who are so enthusiastic to learn these things. And a warm welcome to our chief guest, our beloved Prasanna. He told me, don't call me sir, and we are my sister, and Prasanna. And before that, I want to hear something more about from this, getting this Prasanna to this occasion from our Pudisa. And I want Pudisa to speak a few words before that.
Thanks, Fajil Marsh. Today is a wonderful day for more than one reason. One is it's a Teachers' Day. See, we pay up our respects and remember the role played by the teachers in the life of each one of us. Secondly, we have today a young person, a young scientist, a highly achieved scientist of VSSC in our midst. He, as Shajil Marshall introduced him, he has been in the composites group of VSSC, heading a division, and he has come. One thing I think probably missed is that he is an ME from Indian Institute of Science in aerospace area. So coming through his pathway of progress, tends to diploma, to degree, BTech to MTech, IAC, is something a strange route which normally a scientist takes. So I was so much excited in seeing it, and I, as a HR director of ISRO, I have seen the people who have come through that. There are few, they have done exceedingly well in performing their roles. So that's why it's a that today is that kind of a day to get a rare person of that combination. And one more thing I wanted to say that today the beginning of VSSC scientists who are working, coming and addressing us. We are going to have few more. Two more names have come from Director VSSC, Dr. Somnath. Dr. Somnath has been so nice with our Space Club students, and whenever they visited LPSC as when his directorship time, VSSC when he is now director, he has treated our student extremely well and tried to give them the best kind of picture about space. So we are going to have two more speakers from VSSC and some more may follow. So that way, this is also a beginning of a day of going to get working scientists from ISRO. Third is this composite group is a group which nurtured or which was nurtured by Dr. Abdul Kalam. He worked there in composite group and gave a very good foundation, strong footing to it. And I know many veterans of this composite group, C.R. Satya, so several of them who are doing exceedingly well even after leaving ISRO. So, my dear students, please make very good attention. Listen to Mr. Prasanna. He is specially chosen to address you by Director VSSC Somnath. I understand he has very selectively chosen Prasanna, and we are going to have a few more. Shanid is going to talk in one of the thing, and Rajiv from SPL, they are also going to come. There are chosen few in VSSC who are selected for this kind of roles. So that's why today is a very, very important day, and I request Prasanna to present his talk, and let us wish that we are going to get you more frequent, more and more occasions. I want to frequently more and more occasions, and when Corona leaves and we are able to see face to face. Thank you.
Thank you, Kuti sir. Before that, we have one direction to all, that all of you should type your name and your position or occupation in the chat box. We want to know who are sitting here. That's why we want to take a feedback of that. Okay. I think all of you will do that. And welcome Mr. Prasanna to present his wonderful presentation.
Thank you, Kuti sir. And absolute thanks to Bharat and Shajil. I hope I can address them with those names. They have become a good friend in the last 2 days.
Sure.
It was very kind, and felt honored by the words that is spoken. And he even before I could present, he said it's a wonderful presentation. That's a fantastic initial condition for a mathematical equation. Start with a very good constant. Then you can always play with the constant. So he gave the initial constant a very high value of wonderful number. Just start with when I try to present, I will not just show a PowerPoint presentation. So it won't be a simple opening the PowerPoint presentation and showing my slides. So instead, I will be sharing my entire screen. So your entire screen will be the playground for all of us to watch around. This is not going to be a lecture. So we will be traveling together with all. So I may be traveling sometimes slow. I know that students are the fastest. So I'll try to catch up with your thought process. Maybe as we go into the presentation, you will understand the meaning of these words. So I hope I'm audible enough. Any corrections to be required, you can please suggest on the way. I hope I can start now. So I'm presenting my entire screen. You must be able to see my screen. If anyone can. Okay. So before I start the PowerPoint, I'll just show that how a sine function is part of our life always, and it will be a sine square function which is more closer to our life. You can see close to the zero, it starts very slow and it starts picking up. That's the way my lecture will be, or my talk will be. I'll be stumbling a lot in the initial phase. You will recognize that, and slowly pick up and reach hopefully a cusp point. The cusp point, instead of pi by 20, it may happen around not even at pi by 4, around pi by 2. Then beyond that, you can see what happens. But I will avoid going to a cubic function. You are seeing what is happening. So that we will avoid. So beyond the point where it intersects the x-axis, we should be stopping. Why I didn't choose sine x is close to zero location, it has a higher slope, which requires a good energy to start with. I'll be starting with a slightly energy conservation route. So this will be our mode of presentation. And this is also part of attention. If you see, the attention initially will take some time because we try to align ourselves with the speaker. And as we keep moving on, there will be a peak point where we both, the speaker and the listener, will get well aligned. That's a cusp point or the topmost point beyond which we should understand each other and move forward with our time. I will also show I have traveled much beyond. You can see this you can even come across in your daily life as you drive your vehicle through a road. You see a sharp bump. Many of the Indian roads, they use sin x as the start point. Sin x, you can see it has a sudden change in slope close to zero, which is not good for the vehicle. Sin x square, there is a continuity. It gradually starts. So that is how even the bumper in a road should be designed with. That is how everything in our life should go with. It should start with a nice continuity, pick up, and go to wherever the cusp point that we want. So with this thought process, I'll just go into the start of the presentation. You must be able to see my screen, PowerPoint screen. So it is, of course, a honor to address students in this great day. Addressing adults is easy because their time is more available, but students' time is a very precious time. And getting their time, Dr. Radhakrishnan, he said you should use students' time to the best that you can. You cannot afford to waste a student's time. So at this juncture, I'll just give a quote. When we think we know, we cease to learn. So, and students are the best example of this. They are never satisfied with what they have learned. So they never are feeling a completeness. So they always crave for knowledge. So I wish I will be a student for my entire life. I hope all the elderly here will agree with me. With these thoughts, we will enter our presentation. So I will assume and pray the Google and my BSNL network are merciful, that I saw in the previous presentations also. So I hope it continues to be so. And you people are ever merciful. This is a prelude. At the end of the presentation, you'll know why I made this statement. The one more reason is I'm not a regular orator. I'm just interacting with maximum of 5 to 6 people in my division every day. and they don't listen to me for more than maybe a few minutes. So making a set of good students to make for listening to a large time is not an easy task. So unless you be slightly merciful, so I'll just before and put you to that. Neither last week lecture, Kutisa invited me, and I could watch a beautiful talk by IST professor. Obviously, he's a professor and showed his class. Here, I'll be mostly making up for that with few technological aids with me, because whatever I could not tell by words, I'll try to show by other equations. So it may require a lot of switching of my screens. That should be causing slight of a chaos as part of the presentation. So you can be slightly be receptive to it. And it's only a request. So that chaos will be part of as we move along. And in nature, chaos is always ever present. So it is good to get tuned to it also. As I said, demo switches will be there as always. So with this, we'll go into it. So once upon a time, there were three people: an engineer, a physicist, and a mathematician. All three were traveling in a train, and they were looking through a window across a nice field. And they noticed something: a black sheep. The engineer immediately got excited because for a long time he was not seeing anything, and he started shouting,
Prasanna
"Oh,
sir,
yeah.
you have to present it one more. Somebody has interrupted and you have to present once more.
Oh, okay. I can do that. I can do that. Yes.
Shajil sir, can I please interfere? There is an important tip that I gave to the participants beforehand. Let me please repeat it. So, if in a few moments, if someone else tries to present, again we'll be losing the presentation of our speaker. So, for not losing it, let me give you a tip. When Prasanna sir presents once again, you can see someone. You can go to the people's object options. You can see two options which are seen in the top right corner: chat and people. Go to people and go down, and you'll be seeing something called Prasan Veni presentation. You will have something called Prasan Veni and presentation inside brackets, so parenthesis. So go and search for it, and it is presently not there because Prasanna sir hasn't presented. When he presents it, go and click on it. So you can click on it and you'll see something called the pinning option. You'll see a symbol of a pin. Go pin it and you won't be losing the presentation. Okay, so Prasanna sir has presented once again. If you go to people, you'll be seeing something called Prasan Veni and presentation, which is given in parenthesis. So go search for it and pin it. Over to you, sir.
Absolute thanks, Bharat. Thanks for. I saw your patience last time itself. I learned from you, and I hope you are able to see the presentation on my entire screen again.
Yes, sir.
Okay, I'll continue. So once again, thanks for being merciful. Oh, sorry. We were in part of a story, and we were in the excited condition of engineer shouting, "Sheep in this place are black." Physicist got a bit annoyed. He said, "No, you must be clear in your statement. Some sheep are black in this place." So mathematician became extremely annoyed. He just said, "You must be very clear in what you say. In this field, there is at least one sheep which has one side black at one point of time when looking from this position." So that is what mathematics can bring into your statements, whatever may be the life you lead. You can see here, he brought into the concept of count, the number system, the concept of time, because with time things can change. So he froze at the time. He was very particular. So time has been brought in as a function as the observation. Then the orientation, which you people must be familiar with the coordinate system. So orientation also, which decides how we observe it, the observer's orientation. All these are brought into by mathematician. So just to say, these three people are not independent people, are part of us, each of us actually. It is up to us to decide when we have to evoke who to what extent. Of course, you cannot always be a mathematician. You have to be certain times of various, you have to generalize few things. That also we will see as we go along. But this is what the mathematician brings into our own. I will show you a small example how this preciseness matter, because mathematics is all about not being just precise, getting to know when to be precise also. I'll show you a simple example when we had a problem of being a slightly lack of precision. So I just, as we move along, I will use some of the clippings that I have taken from your textbooks. I used 11th standard as average, 10th and 12th I understand is the student range, so 11th as average. I just picked from your NCRT 11 chapter 3. Here they have mentioned use approximate value of pi as 22/7. Let me show you what happened when we use this for one of our calculations. As I told you, I'll keep switching. I'll be using certain mathematical tools, which I will share you at the end of the presentation. So this entire my screen will be your playground. So you can see whatever I see. Yeah, effect of approximate pi. You can see that 22/7. The left hand side, what you see here is the input, this software. The blue guy is the output of it. So that is the arrangement here. It is like left hand side, you can see as everywhere is the input, right side is the middle one is the output. Okay. So what I have done is 22/7. If I run, you can see it gives an output of 3.1428, and okay, to whatever extent we want. That's okay. And let me calculate the length of a circle, which means the circumference of it by this. Let me take 1 as the radius. As you all are far ahead of these things, 2 pi r we know as the length of it. So 2 pi r, I will just run through it one by one. Execute it. It's executed already for you. So 2 pi will be there because I have assumed 1 as the radius. And this here I have used the inbuilt function pi. Let me use that approximate value 22/7 here. It has given some number. So the difference between these two, as you know, is the error. Let me find the error of the length. Error in the length is actual with using the highly accurate pi and approximate. Let me run through it. The difference is of the order of 0.0025. It seems to be a very, very small number. That's okay, negligible as an engineer may feel. But let me put some units to it. Let me run to it. Instead of just 1, let me give it as 1000 mm, which is 1 meter. Let me take a 1 meter radius ring. Actually, this happened to us. We want to have a stock of a rod to have a circle or a tube out of it. So when 1 meter is the radius of it required. So when you run through it, you can see 2 pi r. It gives some circumferential length. So this is the length you are supposed to take the rod. But when I use 22/7, I end up with this condition. So as usual, now I calculate the error again. Now the error is 2.5 mm. So after I bend and try to join it, I will not be having enough length. So there will be a gap of 2.5 mm, which is substantial with the kind of accuracy I need. So 22/7 is okay as long as you are okay with the first 2 digits. As you want to have a higher accuracy, you have to go for a more deeper precision. Let me show you a better approximation for pi. Up to 7 digits instead of 22/7. Use 355/113. That's an interesting thing. These are all Srinivas Ramanujan's beauties. He has approximated pi fantastically. Just by these 2 ratios, he gets pi up to the 7th digit, the accuracy. So that is substantial. That is in not even micro. It is in the nano level. Up to that, you can get accurate system. That is fine with us. So this is a better approximation. So this is only a classical example. I just run the same code again. Here you can see circle length maybe to show that it's running, I will just do one thing. So for you to get a feel of run. Okay. So now the error between these two is 0.000532 mm. That means these three are micro. This is in nano. So it is only some 530 nanometer kind of error, which for me as an engineer is tolerable. So that is what mathematics brings into it. And that is where precision is all about. Now we'll go back to our presentation. I'll keep closing as we progress so that space is okay. Back to here. Let's start with drawing with some simple geometries. Yeah, I think that's already done. Yes. Y is equal to function of x is something all you guys are exposed to. My language will be slightly assuming I'm talking only to students. I hope other elderly tolerate and accommodate that, because it's fun to always interact with students with their language. If y is equal to f of x, a simple y what it means is as x changes, y changes. What extent the function defines it. So assume x changes from some value here, as I mentioned here, -1 to 1. What happens to y? Let me start imposing certain constraints. That function is a constraint basically. Let me start with the y is equal to m, which means y is equal to constant. There is no change happens. If y doesn't change with x, what do you expect if I plot y versus x? No change. So it must be invariant, or it must be constant, or a straight line. So I hope you should be able to see this highlighted line. And you can see that it is at a height of 3, because I have given the constant to be 3. Of course, you can play with it in the constant. Now it will be at 4. Y is equal to constant defines a line. It's very trivial, isn't it? For you that who are studying advanced things, this should be straightforward. Let us start with it. As I told you, we are using sine square x curve as we get your attention. Let me start adding some beauty to it. So instead of just using m, let me modify that function to be m into x. Now x is coming into the play. So y starts behaving as a function of x. Previously, it was not bothering about x variation because it was a constant. What you should expect? A line, of course, but it is a rotated line. The geometry now, which was a horizontal line, has started rotating. So you can see that m is a whatever acted as a mere translating element has started acting as a rotating element. Let me show you that by changing the m here. So here you can see it is varying from y-axis 0 to 4. As I have changed the m, 0 to 10, of course. It has only amplified, actually, not rotated, basically. I can keep playing with it. Let me put 0. Of course, you get the x-axis. Let me keep increasing. I just keep extending it. Right. So back to my 3. Now, what if I combine these two? I initially told y is equal to constant, then y is equal to a function of x. This guy not only just rotates, because m moves the line, mx rotates it. So combining these two brings into the concept of translation and rotation into our world. You can see that what was going through the axis, now it has got translated because of this m guy, and that mxi caused the rotation of the line. Here too you can play with it. I make it 0. I bring it to zero origin. I keep it m. I make this guy 0. You can expect it to be a horizontal line. So, they slightly expanded the world by having both translation and rotation we brought into it. Now, what will happen if instead of x, I start going for, instead of, I start bending it? That is what the x square brings into it. It starts curving. You may have nice names for it like parabola, but basically it is like adding one more multiplication factor x to it. So which bend or curve out? So we started with the unbent horizontal line, rotated the line. Now we started to curve that line. Having curved it, what next? Go to x cube. Let us see what happens and observe the behavior. We have twisted the line. Whatever was nicely existing in one plane, we have started twisting it. So we have got the line to do whatever we want by playing with these exponents. You can keep adding more exponents to it, but this is a good enough start. We will go back to and we can start enjoying what it can do our world. So here in this geometry, you can see there are at least 3 y is equal to constant. The 2 eyebrows, which are y is equal to constant, and the nice mouth line, which is also another y is equal to constant, but different constant, so that is at a different position. As of now, don't bother about the circles. That circles we will come back to it as we move along the presentation. Now let us apply whatever nice simple manipulation we tried on this. I just go to, of course, yeah. I just avoid. No, what if I add y is equal to x square to this world? Let me see it. Y is equal to, no, not the minus x square. Please go for plus x square. Okay. Yeah. So adding a x square to your life changes it a lot. Of course, minus x square also is required because we are having a sinusoidal life. So be ready for either minus x square or plus x square as we move along our life. But that's not all. We have a wide range of things to do. So let us start doing that also. Let me start becoming slightly curious. Yes. And let me start being happily curious. And let me start being dynamically curious. And of course, all these manipulations you have already seen. We are just doing y is equal to mx plus m. That's what we are doing here. While y is equal to x square in the mouth is fixed constant. So back to your condition. Back to y is equal to constant. Back to y is equal to constant. Of course, that is not all the emotions that you play with. So you can always afford to be. You must be able to relate now what I have done here. It is y is equal to x cube. So it has brought in twist to our life. Of course, when a twist happens, our eyebrow should not be just looking at it. It should either respond angrily or it should respond coyly. Of course, you can be perplexed also as we move along. Okay. So you can keep playing with these emotions forever and ever, just using the first 4 terms that we just saw. Nothing more to it. Yes, we are back. We will keep using this guy as our guinea pig. He doesn't bother it. as we move along. It will be he's a nice guy actually, because he's all curious always. So we saw the mood changes when we added a x square to our life. Then we had a dynamism to it by wearing the M. Of course, I didn't show it. It is all possible because there are wide things you can play with. On all these, we are just playing with only two things. The coefficients. Coefficients are nothing but the constant term that comes before the x square or x, what we just saw, and the x exponent. Only these two we have been playing with while we covered this entire emotions of our life. Of course, there are more emotions to it. You can combine x square and x cube to add more emotions to your life. Yes, yes. By just playing with the rotation of your eyebrow, you change your angry frown to your coy frown, of course. So, by simply playing with polynomials and coefficients, you see that, as I mentioned here, next time you see someone, your friend, you can see it's just a polynomial series, and that too of not a very high order. Up to third order is sufficient to just model your friend, see his mood, and play with his mood. Of course, join with him in his mood. And this is nothing new that I have brought into the lecture. This is once again a snapshot from your 10th standard book, of course. So you're seeing that ax cube plus bx square plus cx plus d. Here, at least in whatever I showed, I use the same constant. You have gone to a further extent, having different coefficients also. So all the emotions you have captured in your 10th standard itself. You have mastered it at that condition itself. So with that, we'll move forward. Now, how does it play a part in what we do? We were talking about human emotions. Material also has emotions. Material also has behavior. How do we understand material behavior? Because that, as part of our either rocketry or whatever we do in a daily life, we play around with the materials around us. So unless we know the behavior, we cannot play with it. Unless you know the chair where you sit is strong enough, you won't dare to sit on it. So you must know the material behavior. How do we understand the material behavior here? By giving input and studying the output. Like we saw, y is equal to f of x. We change the input, we study the output. Y is the output, x is the input. That's what we do in our case also. Only that we use forces instead of words for humans. So humans change their behavior and emotions with words, while material does that with forces. That's why we are often advised, be careful with your words. So that is because the big force to play with human emotions. That is what we do for playing with the material emotions. Take a simple case of just a spring. I am loading it. As you see on the right hand side, when I apply a force to it, the spring expands. Assume as of now a very, very simple behavior. Linear behavior. Linear means f is equal to kx. You can easily relate it to y is equal to mx that you saw. And immediately you can see the geometry. Y is equal to mx is nothing but a line. Only it's a rotated line. That's it. Nothing more to it. That is how we also try to understand. We just apply a force, see the behavior, fit the behavior for the material. So each material we generate what is its behavior by applying a x and seeing the I'm sorry, other way, by applying a f and seeing the x of it. That way we construct a geometry. In most cases, a linear behavior exists, but of course, nature is a highly nonlinear system. You will see that you need x square and x cube also to understand it. I'll show a simple example. Some of the material that I work with comes under the class of brittle material. Don't bother about the terminology of brittle. It is nothing but y is equal to mx because it's a straight line behavior. But you know that plastic is not so strong material. And beauty of plastic is you would have seen that when you try to carry a heavy thing in the plastic, initially it may look like it is taking the weight, but as you keep carrying, as you move along, at some point of time, it fails. Often we encounter carrying our vegetables and other things, what we put on it. So it has a non-linear behavior as you see here. And you can easily relate to the geometry. It is nothing but a portion of y is equal to x square only rotated by 90 degree. So that can be approximated to a y is equal to x square condition. Between these two, there is one guy sitting which does not belong to simple y is equal to x square nor y is equal to mx. That guy we will slightly attack in more detail to understand. So this is the way we understand the behavior of materials, like you did in the previous slides on the emotions. This is a terminology which I will slightly carry on. Composite is a material that I use. I will expose you to material as we, as of now, just take that this material is quite strong. Strong means it's stronger than even steel. And that is why we use it for designing structural products for our satellites and launch vehicles for certain class of because it gives a lot of advantage. It first minimizes the size because its strength is very high, and it makes the thing lighter also because it is with a low density. Less density, and being lighter and being stronger is fantastic combination that we use in our design of it. I will come to it in the later slides showing more about it. As of now, just take it. It is nothing but a simple y is equal to mx, what I work with. That way we can connect to each other more easily. And of course, plastic is y is equal to mx square, as you saw here, the nonlinear behavior. Let us go into the behavior of materials now. Yeah. So from humans to materials, we have started switching over. Same, we will carry over our friend M here also. I'm just going to plot two things. I will slightly zoom it. I hope it's visible. Yeah. Mx should be a line. 2mx should be just another line, only amplified. So you can think that the second guy is our composite, which is going to be a strong element. The first guy is a steel. So when I try to plot this, you should be seeing two lines, of course. Oh, sorry, I have not given my friend a chance to run. Okay. Yeah. This blue guy is composite, which means for the same, if x-axis, you can read it as stretch or deformation, or y-axis as the force. It requires large force to undergo same deformation. This guy requires very small force to undergo the same deformation. So I always will prefer this guy for my structures. And that is defined by simple mx, what we just saw. Now let us add more life to this material behavior. So I am becoming more clear about it. M for composite, M for ion. Now I'll run through it. So sorry, I have already run it for you. You can see the difference which I just showed. Now add some plastic to our life. So it doesn't look so, yeah, I will zoom this so you can see the nonlinearity that is in the initial phase of it. Now I hope you can see that it's curving out in the initial phase, capturing the plastic behavior that I just showed. So to bring that, all I need to do is m square root of x. The reason why square root of x is I had to rotate it. I could have as well played y is equal to x, but it would have, I will show you that also here real time instead of this. So I think these guys are spoiling the. So I'll add a 0 to these people. They don't interfere in our graph. I made ion and composite to be 0, so I can see only plastic behavior here. You can see. This is nothing but our smile, but one half of our smile, which is y is equal to x square. To rotate it, I just add a 1/2 or 0.5, whichever. I just curved it the other way. Now when I added among bringing back this composite and ion back into the picture, these guys are extremely strong, so they exist here. Plastic is not so strong. So with these same equations that we saw the emotions, we are able to capture our material emotions also. Of course, with some approximation. As I initially told, we can invoke our engineer or mathematician or physicist. I will be doing that as part of this talk at various phases. So plastic, you can see it as a rotated smiley with an exponent non-integer. Usually, when non-integer becomes exponent, it doesn't come under the class of polynomials. Polynomials is which has integer exponent, but we will not bother about such purity in this, because here it's more of an understanding that we will go behind. Now, happily, we have just drawn these curves, but we have not drawn a nice middle curve, which was showing a lot of changes. So let us try to capture that also. This is what we saw. Now, how do we do this? You can see this as three phases. I'm just highlighting it, so what I'm talking about, you can see. This middle guy, which has ductile material, which is listed, which is not a nice, but you can see a portion of it up to some point, it is a straight line. Then it has a negative smile, a positive smile, and then once again a straight line, and again one a positive smile. So by combining the equations that we read, that just we saw, we can build a overall behavior of it. That is why we usually use various terminologies: piecewise integration, piecewise polynomial, piecewise fit. This is nothing but piecewise addition. That's it, nothing else. So you can capture any behavior that you want by locally understanding it, fitting your equations, which is straightforward: y is equal to mx, y is equal to mx square, and so on, to build any complex behaviors, or seemingly complex. There's nothing complex at all if you try to understand what is its differential part. So I will just show. I just tried before this talk, experimented with it. This may look like you just read it as x cube only. This is just an offset so that I can capture this, whatever bump you see, up bump and down bump. So I just offset it a bit. Otherwise, it is nothing but a cubic term and a square term, which is cubic and quadratic term in another terminology, and added few translation and a constant. So now we can see it nearly captures whatever the behavior that you see here. This. So along with this, if I add initial y is equal to mx and the final y is equal to minus x square, because it is a frown what we see here, then we could have captured the entire material behavior. This is a typical behavior of steel. So now you can play with steel when you go near it. Of course, you must apply corresponding force to understand this behavior. So generate enough strength for it. So that is what I just shown here. Having understood that human emotions and material emotions are governed by the same equation. That's why a mathematician doesn't care about applications. So he only cares about the basic underlying mechanism. You can apply it to infinite applications, what you see around. You may be working as a designer of a product, whether it can be in a toy industry or a space industry or whatever industry you can think of. You can apply the logic, a mathematician's logic, anywhere. We need not get disturbed by the application, which may misdirect you many times. That is you can often, maybe in the course of this talk, I will highlight where such misguidance may happen also. So with this, I'll just move back to. As I told you, this what you see here, the black. You must be seen our at home people stitching. So they use bobbin and a thread. So composite is very similar to it. Composite means it is made of two components. One is a fiber and a gum, which holds the fiber together. So this fiber is in the order of microns. So they microns means talking about the diameter of it. They come wound like this. This is what I work with. Such materials we receive and we apply it over a component. I will show you that a simple video. I hope you must be able to see a real-time video. What you see in the black is a spherical vessel. Over that, you can see this fiber getting nicely placed. This is a material addition process. So this fiber is nicely getting laid on it to build the required thickness. What basis thickness is decided, that we will see as we move along. But this material
Sir, there is a problem with you? Hello?
I'll run through it. It's a very beautiful operation. It's called a filament winding operation because the rope or fiber is considered as a filament, which is wound over a surface. That's why beautiful terminology is coined filament winding. It has very deep mathematical logics. Maybe we will try to touch a bit of it, which itself will be beautiful. So I'm just closing it out. Okay. And feel free to stop in between because these kind of webinars, I see that since I don't see the reaction. So sometimes I may not know that whether a presentation is going through. Please interrupt me if there is any hindrance of it. So I'll upload the. We have seen that human emotion and material emotion belongs to the same category of mathematical emotions. So we play with the same. So not only when you see your friend, when you see a non-living thing also around you, you can rest assured that you can easily understand his behavior next time. It's only a simple polynomial series. Now you also extend your imagination for a slightly seemingly complex thing by combining many polynomials. So it's piecewise polynomials. So you have started capturing complex emotions, or for me, it is complex material behaviors. Now, as a further extension of it, where do we go? There are some natural questions that you can ask. What time the behavior changes? For example, the human behavior, we are very intuitive. By seeing a face, we can see at what point, as a young student, when we tell some
Prasanna sir,
yeah.
there is no, the presentation is not visible now, sir.
It's not visible, is it?
Not visible. You have to represent it.
Oh, sorry. Okay. I will do that. I'll do that. I'll do that. Is it okay now?
It's okay. It's okay. It's okay.
And I hope I can take up from the same point where I left. I'll just quickly go through it. Yeah. As I was just mentioning, as a student, as we try to give excuse to our parents, we know up to what point we can keep driving the excuse. When behavior, seeing the facial behavior at one point, we'll stop giving excuse and simply say sorry. So we should know where such changeover should happen in our submission, whether it is a human interaction or a material interaction. So that is the next natural question. We saw to capture the behavior, but when changes happen, that is the next question that we should ask, and extent to which the change happens. I will show with an example. This is also the need for understanding derivatives and roots. So here you can see I just took out the nice curve of our steel. You may, as a material designer, you may not want to go beyond the first hump, because then you don't suddenly a change in your geometry, you will not be happy. You may first want to know when the first hump happens. So you may want to live within that period only. So how do we find where the first hump happens? We will go with the thought process. That is the region I should first understand when that region happens. So if I know that when that region happens, I will try to live within that region or go past that region instead of just going and standing in that region where things are quite unstable. So how do I know when that region happens? Imagine this entire curve that you see here is made of very small lines. You can always zoom in and you can connect things with you may have also constructed circles by multiple lines. So in the same way, you can think this entire curve is made of small line segments. As you know, line segments is mx, and okay, if you want, you can add a c to it. So this is a small line segment, and I can keep traveling along this. One more line segment, keep traveling. Next step, you see that it starts changing direction. It may be a tolerable change in direction, but as I keep continuing along the small line segment changes, you will soon find that the direction will be flat, or it is a point which in other mathematical terminology we say slope. The slope becomes 0. So this is what you must have also read through in your books as maxima point or extrema point. Those are all just terminologies. Otherwise, it's merely that reaching a horizontal condition. So from that horizontal condition, it's either going to go uphill or downhill. That we will not bother, but we will try to understand at what point it becomes horizontal, and we'll try to live before that. So for that, what is the condition? The slope should become 0. Let's try this with this example. Oh, let me directly go to it. Yes, I have it. Okay, I just took the same curve here, and like we did in the previous the couple of minutes back, initially fit a behavior to it. So we fit a cubic plus quadratic behavior to it, plus some linear and constant. So we captured that region. Now our interest is where the slope, as we move along this behavior, where the slope becomes 0 or when it becomes horizontal. That's a maxima point, local maxima point, for which I will slightly make a small jump, saying I will do a, sorry. Okay, it's correct. So what I've done is merely plotted that local behavior. I'm interested in the maximum point of it. what I did was, for those lines, I can get the behavior of the lines by taking the first derivative. This is the only region where I will slightly live with the class 11 and class 12 students. So this is the only place where class 10 students can slightly forgive me. Derivative is nothing but getting the change in behavior. Okay. So as we saw, the line changes. So that change in behavior can be captured by derivative or slope change. So this is the only region where I will slightly jump. So I have found for this behavior the derivative. So this is what you see, how the line changes. Now our interest is, as this keeps changing, when this line change becomes 0. So I have to simply equate it to 0. That's what I have done here. And I am solving it for, so this is nothing but when I will also do you one more thing. I have done in the bottom, sorry, it is there already. 0. Oh, I didn't run through. Let me run through this. Yeah. I have plotted. Yeah. Oh, okay. I wanted to show you what is this tangents also. So this is what, as we kept moving along the curve, at one point it became nearly horizontal. That is the local maxima point. So that is what we are trying to find by taking that its slope is 0. So having made the slope 0, solving for this equation, I get two solutions. This is nothing but, whatever we got is nothing but your quadratic equation. You have solved a more complex problem. This will be very straightforward. But it is the same concept we use for getting the material behavior also, where the material behavior changes. Simply take the derivative of it, equate it to 0, and solve that quadratic equation. So it is going to give 2 points that I'll show you. Those 2 points are correct. I'll zoom this and show that, or maybe I will show it in the first figure. Yeah. So what are the 2 points it was showing me? Max, it is at 0.2 and minus 0.46. That you can imagine here. So it is close to this region. That is the first happens. And it also captures where the minimum change happens. That is this 0.2, what this region happens. Because that is the region of my max and min condition. So both these places, our line becomes horizontal. And that is what we have equated to 0. So from this we can see how you must have solved many problems finding the solution of quadratic equation or finding the roots. So what is the use of it? The use of it is to find the behavioral changes, whether it is for humans or whether it is for materials. That is what is the application. And for any change that you want to understand, all you have to do is initially fit a polynomial or similar thing, find its change, and when the maximum change happens, and use that maximum change to play with your design. This is what we do. I have also plotted that it is our smiley actually. And this is nothing but a snapshot from your 11th class to say that nothing new I'm showing. It is whatever you have going through or gone through or only this kind of curves. Now what do I do with this data? Once I get the maximum change, what I do with it, I'll go to the presentation and show. Let me see how I use it. On the right hand side, what you see is a cylinder in which high pressure, what is shown is nothing but gases that gets formed when you burn a propellant, and that tries to escape. On the one side, it's closed, it cannot escape. It's going to escape through the other side, causing a propulsive behavior. That is how the movement happens. The physics of it, we will not go into it. We will enjoy the mathematics part of it. So how do I know what is the highest pressure that gets generated? Because I have to design my vessel to hold, design my vessel or cylinder to hold that pressure. If I don't do that, it will be an explosion rather than a propulsion. So usually, yeah, pressure time curve, like we saw a force displacement curve, a pressure time curve is generated. Pressure time curve is merely to say that with respect to time, what will be the change in pressure inside the vessel. So you are seeing that the nice curve. It need not nicely come into a polynomial. Later we will see other ways of modeling this behavior. But as of now, our interest is at what condition the max happens. Our interest is this location. So to capture that, whatever we just did, what we have to do, nothing more to it. We just have to fit the equation, find the derivative, find the root of it. That will show you at what point of time what will be the value, what will be the pressure value. That is what goes as an input to my design, because I told you I am designing pressure vessels. So that pressure is given to me. Then based on that pressure and the material property that we just designed some time back, composite y is equal to mx, we captured the behavior. With that behavior, I will try to find what is the total thickness the vessel should have to take up this pressure. So that is how the connectivity goes. And as you saw, all this from your 10th and 11th, what you have done, nothing more. Right? And when you violate also, what happens, I will show you. In enthusiasm, I was trying at home. As you see the effect of it, it was not, this was a alcohol rocket I was trying at home. It was not, there was only a combustion happening, a small fizzing of it. So I started reducing the whole dia on the cap. At one point, the whole dia was so small, the pressure rise was so high, you can see the bottle condition. So unless we understand it, this is will be there. So of course, I improved upon it. Also, that we will see the video here. What you see here is a bottle with a slightly vaporized alcohol in it. You must have tried it. This is a space club, so you might have tried even better things. I will go to, yeah. So it's a nozzle-like arrangement. That cap has a hole for the gases to escape. You can enjoy. I'm holding a candle nearby. And this bottle is not a water bottle, because water bottle thickness is less. It is a one of the fish drink bottle that I just borrowed from it. Actually, I wanted to show you such demonstrations during our interaction, but this webinar doesn't straightforward allow. So whatever possible, I will show you as a demonstration. One important thing to note is, if I had used a water bottle, it is not, thickness is not designed to hold the, handle this pressure. It would have exploded, not propelled. That is what happened in my other case also. That is how the importance of your maxima goes, whatever you see here. So you must understand the maxima, design your container or vessel. If you are doing model rocketry, accordingly design your thickness and ensure that you have a nice flight. This is the connection goes. The bottom is what I have mentioned, including our pressure vessels. Yeah. All this we do in our daily life. But till now, whatever equations are solved are the foundations for all the things that we are doing now. To capture your imagination, not only the small bottle, what I show here is a snapshot of third stage motor case. Okay, now it is slightly evolved also, but sometime back this was a third stage motor case. The motor is nothing but the golden bottle that you are seeing. It is a filament wound vessel. Just like the way I showed you a video, it is wound, fibers wound. Imagine it is just a weaving technique which builds such beautiful structures. It is filled with propellant, and the bottom you can see a nozzle through which the exhaust flows out. This goes into the third stage of PSLV. This vessel is designed with such logics where pressure a team works on to get the maximum pressure by finding the maxima, which goes as an input. Based on the pressure value, design the thickness with our composite property. Similar bottles you can see on the bottom also, which goes into various phases, including satellites. Yeah. So quick takeaway, it's not going to end, it's a quick takeaway. Now we can fit model to any behavior. That's what the model means. Y is equal to mx is the model. You can change your model based on the behavior. You can see on the right, mx plus m for eyebrows, x cube plus x square for your twisted mouth, and so on. You can fit your own models. And you can always slightly expand your thought process. Till now we have used only y is equal to f of x. What if I add one more dimension to it? Z is equal to f of xy. So from a line, I am going to a plane or a surface. So you can start playing with the one dimension higher. I will show you a simple, yeah. What you see here is a plate. I will try to slightly zoom so that you enjoy that. Y is equal to, you can see left hand side, it is merely a polynomial in x, y and z. You can see that its order also in 2, 1 and 0 only. Nothing like our equation we just saw previously, x cube, x square, x and constant. Only we have added one more dimension to it. Now what are things we can do with it? I just changed the x square. Previously we were getting only a parabola. Now it is an extruded parabola because it's a surface. Let me start playing with the parabola. Let me change. All I'm doing is changing the coefficient of that polynomial equation. So I will show you some beautiful geometries that comes out of it. Yes. And I presume these are all dynamically you are able to see because I am assuming all these are dynamically getting updated. If any one quick response may give me some confidence. I hope all this, whatever I'm just showing, you are able to see dynamically. Bharat or someone can just give a confidence that the presentations what I'm just showing.
Yes, visible, visible.
Okay, dynamic change you are able to see, isn't it?
Yes, sir.
Okay, thank you for it. So instead of just playing with a line where we twisted it, we curved it, and then we moved it around, we are doing it to a surface now. And only by adding one more dimension to it. So you are now graduating to one higher dimension, and nobody is stopping you with these two dimensions. You can add more dimensions to it. Though it may not be visually or tangible, it's not in physical space. It will be in a higher dimensional space. I will show you some of the higher dimensional space as we move along. I just wanted to show you the beauty of a simple polynomial equation as you move to higher dimensions. What beautiful geometries it can create. Yeah, go back. So this is a polynomial equation which we just played with. You can see it's only the same x square term, y square term, and only we added a z square term to it. That's all. These are the things you read as conics in your class 10, 11, 12. So all these conics are nothing but your simple second order polynomials, only in 2 dimensions, nothing more to it. If we are so happy with polynomials, then our, as I just put here, our chapter 2 should be sufficient for our life. Why are we equipped with polynomials alone? We will see what do we do for such behaviors, cyclic behaviors. Complex behaviors, we saw it can be built with combination of polynomials, but this is too complex to mess with polynomials. I will show you this is not just an imaginary thing. Yeah, this is a geometry which comes out as you move one circle or other circle. In mechanical terms, you can think of a gear moving over another gear. I'll show you as it generates. It's I just put 2 inner gears and outer gears so that you can enjoy the graph. So the point on the gear, what it traces, that is what the path that you see. And soon you can see it becomes more and more complex. And let me slightly play with the geometry so that you can see more and more. Better patterns on it. So such behaviors or curves if you want to model. Polynomials are not the right candidate, as you can easily guess, because you are equipped with a limited set of geometries only in polynomials. So what do we do for such conditions? You can easily guess. It is going to be our friend circle. What we didn't touch in the initial smiley, it is the circular world that we will now enter. So this geometry you can easily compare with, so I'm not going to save it, with this geometry what you see here. And you will encounter such geometries. What do we do to capture such behaviors, cyclic behaviors? Cycle is all around our life. Every morning, sun rises, and every 27 days, the moon cycle. There are a lot of natural cycles. There are a lot of other cycles in our disciplined life, and so on. So when cyclic behavior exists, polynomial does not easily cater itself to a cyclic behavior. Such conditions, we go for our friend circle, because circle is a very one of the simplest thing which shows a cycle. We will use that circle to build such complex models. So let's go back to our smileys. We didn't touch these circles at the time. Now we will handle those circles. Circle and cycles from polynomials is a messy job. We will see how it is a messy job also. Yeah, I'll slightly zoom it. X square plus y square r square, it's very familiar term for you. It is a general equation for a circle. So I'll show you that what is the effect of trying to plot it. If I take radius as 1, it's very simple to plot. You will get a unit circle. Where is my circle? Yeah, here is my circle. Why it is not looking like circle is because the scaling is bad. I will just correct the scaling. Yes, now it's okay. You see, it's generating only one half of the circle. Though I have moved from one extreme end of the radius to other extreme end, which is -1 to 1 for a unit circle, I am getting only one half of it. So maybe instead of minus, I'll put plus. I get the positive half, but I don't get the continuous circle out of this equation, whatever x square plus y square, because the square root is a function which does not give you a one-to-one mapping. You must have read in set theory. What is one-to-one map? For every element here, there must be another element here. So here, for every x element, there is one plus minus y element. For two of y elements, one x element is mapped. That is not a good way to capture the full geometry. I need a more continuous system. Of course, I know I can put a plus minus here and handle it, but that is not good for a continuum, what we want to work with. So let us go for a more continuous system, which is our circle. How do we go to a circle imagination? That can start with our triangle imagination. So here you can see, as you know, for a triangle, right triangle, the x and y is nothing but cos theta and sin theta, if theta is the initial included angle from the center. So I can think of keeping the hypotenuse of the triangle same and just keep changing the angle. So only whatever triangle I choose, all I have to do is cos theta for getting the x component, sin theta for getting the y component. So if I keep continuing by changing theta from 0 to the entire 2 pi, I'll be getting all the triangles and all the x and y's. And if I try to plot all the xy points, it's nothing but a circle. So triangle, multiple triangles, keeping the hypotenuse same becomes our circle. So that's why the equation of a circle is simply sin theta and cos theta. That's all. That is the equation of a circle. That is what we start with. Of course, you can change its radius by adding an amplitude component to it. So let me plot it and show. Oops. Am I? Yeah, it's okay. Yes, I got the circle now. Now I can simply change add some radius component to say, here it is 1 to 1. I can change, amplify it. So I'm getting 3 to 3. I can play with the angle here. So it's now a nice continuum, like the way in polynomials you played with the coefficients. You can now play here with these coefficients to play with the radius and also to play with the x term. In this case, x becomes a theta. So having these are all very straightforward things which you already know. Now comes, what if I start disturbing, like we disturbed the mx there. What if we start distorting the circle? That should be quite interesting. So let me go to the same circle equation, sine theta and cos theta, but I add a disturbing term inside a and b. As of now, let me keep it as one only. So it is nothing but same sine theta cos theta. So let me run through. Obviously, I'm getting the circle, but let me add a text to it. It starts giving a kind of geometry which you saw. I just showed a slightly difficult geometry. Let me start playing with it. For my hint, I just put one. Yeah, this is the geometry what I showed in my PowerPoint as one example. So that comes out like polynomials here also. It's very simple equation: sine a theta cos b theta. That's it. Nothing more to it. So next time you see a column or rangoli, it is a sine a theta cos b theta. We will see more such rangolis here. And of course, I just mentioned you cannot even dare to try this with polynomials. It will be very cumbersome. Okay. So by simple disturbance of our sine theta cos theta, we are able to get seemingly complex. Once again, I am using the word. In the initial phase, it was to when Bharat was mentioning Max is considered as a tough subject. I just wanted to suggest by naming someone as an enemy, we usually make him as an enemy. So better not use the word. Even considering as a Max is a nice friend. So likewise, we will continue to always use the word Max is a good friend. He'll always be your friend. By naming him as a friend, he'll be your friend. That's what we see here. By simple sine theta cos theta, we can build beautiful geometries out of it. We'll see how we evolve out of it also now. Let me add more disturbances and things here. So let me see here. Let me start with one. The one. Instead of using sine theta cos theta, I'm going to use a constant minus sine theta, sine a theta. This I am also trying to do a polar plot. You see what is happening. I will remove the grid lines so you can enjoy the beauty. Yes. So next time you want to show your love to your parents, all you have to hand over them is 1 minus sine theta. That's it. Because when I substitute a 1 and a sine theta here, you are handing over to them a nice heart of yours. You can, of course, change that also. Yes, a flattened condition. You start playing with your bubbles. Can you see where it's heading to? As I just keep changing the n, you are starting to capture nature very slowly. Let me slightly zoom it down so that I run it in the same place. Yeah. As I. So you see sine n theta, the n is a frequency component. We usually use the word frequency. So you can see frequency is nothing but the petals that you see in the rose or whatever flowers that you come across, which comes out of 1 minus sine theta, sine n theta, that's it. So this is the frequency part. So next time when you see a flower, you can see what frequency it exists on. Of course, you can go further and start getting more and more beautiful geometries. And why to leave this guy as it is? We will play with this guy also. Yes. And nobody is stopping us from trying. Yes. Of course, you can play on, and all we are doing is a constant minus sine n theta. That's it. Whatever you started with the circle equation only. You started already capturing some of the nature's components by this simple equation, then think about what are the kind of further areas that you can venture by more of your textbook content. I will show you that you have studied even further to it. Let me move on now. So this one and one what I showed has a nice interesting name also. It's called a cardioid. As you know, it shows the shape of the heart. That's why it's called cardioid. Of course, the second one is usually called a nephroid and so on. And those are all just fancy names to for a physicist or someone. For mathematician, it is always a minus sine b theta. That's it. So let us leave with the flower here. Okay, let us make it. Yeah. Okay, we'll move on. Of course, we saw all these self-interesting things. Now, how are we connected to it? You can see here in the figure, it is a solid rocket booster. It's a section of it. You can see it is a lengthy cylinder, basically. It is filled with propellant, and the white space, what you see inside, is nothing but the space for combustion, for burning. You all are veterans of it, being a space club members. So you can see that from through this empty space, it gives the propellants or whatever the products of combustion through the exit to give the required propulsion. But what is the shape of the uh, propellant which is in these cylinders filled in? That depends on the kind of pressure we want to generate. We saw that pressure time curve. So we can tune our pressure time curve by playing with the cross-section geometry. To the right-hand side, you can see a colorful cross-section. That is one of a sample cross-section. I just picked it. Please don't relate it to any of the vehicles. It's only a sample thing what I'm just showing. It's a sample cross-section. What is the need for this cross-section? You can see there are a lot of in-between empty spaces. So when I ignite it, it ignites all along the entire length of it. So there are so much space available for burning. So I get huge products of combustion and hence a sharp increase in pressure and hence a very high thrust. So I can play with the thrust by playing with this lobe shape. This is called lobe. Each one is called a lobe. Lobe is merely a physical word. A bump is lobe. These are lobe shapes that we just see here. Now you can easily start imagining these lobe shapes we just saw somewhere just above. Here we saw lobe-like shapes. So the same equation should be able to handle an approximation to it, like material behavior you handle with a polynomial. These shapes, like cyclic shapes, can be handled with such distorting a circle. So let us distort a circle to build a lobe shape. So here I am not keeping the r cos theta. See, it's the same r cos theta, r sin theta, what you see here, nothing different. But instead of keeping the r constant, I am just changing the r. Radius changes. So if radius changes as you move along the theta, then it should start giving a waviness. That's what we see here. Okay, I will play with the waviness. So let me start with a simple. Okay, let me start with a zero condition. Why should I? I'll give a 0 here. You can easily imagine r is equal to 1. So I should be getting a circle. Okay. And the scaling, I will ensure that it doesn't disturb you. Okay. I get a nice circle. Let me start playing with the frequency of it. Yes. A nice nut, whatever, the groundnut shell, what you get out of it. You start getting more interesting shapes. There are gearboxes like this for your kind of information. Yes, it starts getting more interesting as I keep adding more frequencies to it. So starfishes starts getting born. And of course, we start getting more and more curious shapes. And we also start getting the objective, what we initially intended, these kind of lobe shapes. So these lobe shapes are nothing but the simple equation of r cos theta, r sin theta, only that r is changing as you, which you can play with. Yeah. Now, having captured the behavior of the lobe, now I can do interesting mathematical things to it. I can see the surface, tangent, and normal. Normals are nothing but perpendiculars to these lines, because the flame are it is going to get eaten away as it starts burning. The propellant is going to be eaten away along the local normals. By that way, I can try to find how the normal is going to go into the system, and based on the rate at which normal is going to, I can, using my other chemical components, I can predict the total components of combustion, from which I can map it to the pressure that is getting generated. So now we are connecting. Previously we just saw pressure max to vessel design. Then how do we get the pressure? That is by still a lower condition, where we are modeling the lobe, from which we are fitting the basic lobe equation, then trying to play with the rate at which the lobe gets eaten away, and hence predict the pressure time curve itself. Of course, this I am slightly simply. As I told you initially, I will be a physics engineer at some point of this lecture, and mathematician. So I am slightly being what is that? Not being rigorous, because our aim is to understand the flow. So I'm not more goes into it in the actual rocket, but this is the same foundation that we require as we build it. So the foundation, what we require is r cos theta, r sin theta, which you have already read long back. I will show you the tangents also. The tangents are nothing but the slopes that as we keep walking along and the slope changes, we can understand by it. It forms a very interesting shape. And to get the from the pressure time prediction we get out of it by getting the normals. So I'll just plot the normals also. There is one issue. Maybe I have not run that properly. Yeah. Okay. I think you have to excuse me. I'll just try one more running the entire thing.
There is some connection problem. Okay. When I contacted him, he didn't know the connection is lost, and he will connect soon.
Extremely sorry that at what point can someone just tell the connection was lost?
Oh, yes, so you have to represent it also.
Maybe could you see that circle animations and
Everything is lost now. You have to represent, sir.
I agree. I mean, at what point it stopped? Maybe I will show you. You can just tell me.
Okay.
Okay.
And one more thing, sir. I think you will say the software you use to make all these things that students
Yeah,
make.
definitely.
Okay,
Yes.
okay.
Yeah, definitely. I think I may also have to hurry a bit because a few more beauties are there.
Okay, no problem, sir. No problem.
I'm presenting my entire screen. I hope all are ever merciful, not only the initial angels, because of these disturbances.
Your presentation is come. Okay.
Okay. Was this slide was complete when
Yes,
I last presented?
it's complete. Filament winding is completed.
When I presented the quadrics of, the whether this was complete?
Yes, it's completed.
When I showed this gear running over the gear to form the shapes of it.
That's we finished. That finished. That we got.
That-
Only one or 2 minutes we lost. Only
Oh, okay. Then good. I am happy at it.
1 or 2 minutes. That's only lost.
Okay. Then whether the propellant shapes that I just showed,
Yeah.
flower building,
Yes. That we have discussed. That was
oh,
discussion.
that was okay, visible?
Yes.
Oh, then fantastic. Then okay, I am happy. Not much is lost. So I'll just
Lost only 1 or 2 minutes. That's only.
okay. Thank you for. I'm very sorry about it. Let me just quickly show that also. Where was I? I hope you must be seeing my presentation. Maybe one person can keep the mic on so that Bharat, so that they can interrupt immediately if you.
Bharat, can you check the exact point he left?
So that
Abhinand is there? Abhinand there? Abhinand, are you there?
I hope you saw all these whatever
Yes. All these
these
were
models,
okay.
and of course
Okay.
that the propellant shape is nothing but your same arc of theta or sin theta, nothing more to it.
I think you can start from there itself. Okay.
Oh, very good. Then nice. There is no beauty is missed because.
Abhinand, if you want, you can trying to have a question, etc. It can be monologue. As he was telling. Okay.
Okay, sir.
So maybe this part I just wanted to just tell we come across many of fixed numbers in our life. You can see 60 minutes, 60 seconds, 24 hours. Why should we fix to those numbers? We have nice 5, 10, 20, 100. Why not we choose that? So I will leave it to you to explore it. Only I'll just mention sexagesimal system is something called base 60. The beauty of it is one of the highly composite number. Srinivas Ramanujan worked on it extensively, composite numbers, finding various composite numbers. What it says is it has lot of factors. Advantage of lot of factors is you can represent its constituents in various ways. So 60 is one such highly composite number, but then why they picked 60? Because at that time they didn't know the meaning of in 3000 BC. They would not have known composite numbers and these kind of factors. And of course, why 7 days a week, 30 days a month, and 12 months a year, and so on. All I can give you a hint. It is based on few cycles, because we were talking about cycles, and nature cycle had inspired these numbers. I will leave it to you to explore and find. You can always ask me later, or we can even discuss after this presentation how these could have influenced these numbers, including the 360-degree for our full circle. Okay, we'll keep moving on. I will show you an example of how we use not only for the propellant and also for the satellite orbit. For a communication satellite, as you know, and I just saw that just 2 lectures back in August 15, excellent lecture was given by one of ex-ISRO mate, elderly gentleman. He had talked about various orbits. So I hope those things are all physics of it are well into your domain. I'll just talk about a bit of max on it. The goal of a remote sensing satellite is to cover the entire surface. That's what you see on the right hand side, a figure. All those slightly dark blue lines are like a filament wound over a sphere. It is similar to whatever I do as a pressure vessel. The same thing is nothing but the visibility of a satellite over the ground. So that's what is usually called a ground trace, the projection of a satellite onto a point on the ground. So remote sensing satellites, it usually tries to see the entire Earth. So they have a different orbit. But for communication satellite, we usually limit it to a specific place. So they are all more aim is to handle only a portion of the Earth. However, equations can help in it. We'll try to make a quick. I think I already opened it, so I'll stop taking my time. Yeah. So what you see here is a good model made by my friend for you. You can see the Earth. If you don't see, please interrupt. No? You can see that the orange guy is our. You can see it as a Earth, and it is inclined to one more small ball here. That you please see it as a satellite. Let me change the inclination. It's very intensive animation, so it may very slowly only update. So I'll do it very slowly. Yeah, I'm making the inclination to near 0. Yeah. So this is with inclination with respect to my polar axis, that axis about which the Earth rotates. Now let me make the inclination very high. I'll take it to the other extreme. Yes. So it is more in the line of. In this condition, if I project the satellite trace on the ground, what is the ground trace I get? That I'll move the satellite and I'll show you. If I have a good relative rotation, of course, RR is relative rotation. You can see it starts forming a nice coverage of the Earth. I'll try to rotate it. Oh, maybe I have zoomed too much. I'll just zoom it out. It starts covering the entire Earth surface, this polar orbit. Instead, I'll bring back the inclination to close to 0, which is the condition for communication. Now you see the trace, which is the blue line, is more limited to the equatorial region. And I will change the relative rotation. Yeah, further I will change the relative rotation. Some more. Yeah. Yes, and a bit of inclination. Yes, it starts playing only in the equatorial region. So there also I just slightly play with the geometry. You start seeing that it oscillates between a specific zone. This is how, by changing the relative rotation between, I will further reduce the relative rotation so that we, as you know, if relative rotation is close to 0, we are going to see one point. That is what communication satellite does. Yeah, geosynchronous satellite, that's what it does. Okay, oh, now I get all the geometries. Sorry about the slow animation, but the point is to show this background equations. What you see here is the same pattern what I showed, the cos theta sin theta pattern what I just showed. So it is the same thing whether it is a propellant lobe or whether it is the satellite ground trace. It is the same equation that we work with as a start point. Of course, a lot of further beautification comes into it to take care of the real physics, but this is a start point for everything. I'll close this my back to ours. Okay. This is usually called as a Lissauges figure. It is A cos nt, B sin mt, which we just plotted to make the flowers also. And this is the similar equation what I use to make the pressure vessel winding also. Of course, you can build more complex curves, or instead of just going around the earth, whatever Chandrayaan did. There too we can go for more interesting equations. Cornu spiral is one, or Euler spiral is one equation, and adding more disturbances to it, we can model the trajectories. So what the aim is, you have to start visualizing whatever you're seeing. I will just show a few examples of it. So I have picked a few exercise problems. I won't ask you to do, but I will do it here. I hope it is open. It's open. So I'll go back to the presentation. Yeah, let's visualize them. I saw in the third chapter of your NCERT 11th class, this was asked, and the question was, prove that the left-hand side is equal to right-hand side. I know that you guys will prove it in just a minute because of your familiarity and your understanding. But one request is you can also start imagining what is that we are trying to do. The left-hand side you can see it's a cos function and a sine function. Inside it has cos of x. Cos of x we just saw it is a wave, and the pi by 4 may just shift it. And adding one more cos to it will scale the other component. It's a multiplication factor which will scale. But in this case, this cos has a y to it. There are 2 dimensions to it. So in the quadrics sometime back we saw if 2 x and y are there, then usually we end up with a surface. If y is equal to f of x, it's a line. If z is equal to f of xy, it becomes surface. So the left hand side is a surface. The right hand side is another surface. We are trying to check whether both surfaces are same. Let us see whether both surfaces are same. I plotted it for you. So I'm putting the same equation. I'm dumping. First, I am plotting the right hand side of it. Sine of x plus y I just plotted. This is the surface I get. So I'll show you convince you by doing it again. And let me scale it properly so that, yeah, 1:1 scale. Isn't a beautiful surface what you see? Sine xy surface. Now let me see the left hand side of it. I am plotting the left hand side also. Of course, hence proved. So now we can convince ourselves that left hand side is equal to right hand side. Same way, I saw one more of your problem saying cos 6x is equal to very high power. We are not even gone to the 6th power and 4th. You people have solved it in your 11th standard. So to visualize this, what we will do is take this -1 on the right hand side. Okay, let me bring it here. -1 on the right hand side. 1 plus cos 6x. Does it remind you of a plus sine n theta, which was building us all the flowers nicely? So all you should expect is a flower out of it. So let me also plot and show you. The same equation when plotted, it gives you a 6-petaled flower. That's why 6x is there here, as you see. That's a frequency part. So next time you see this equation in your book, you must be able to see the flower coming out of it beautifully. Maybe I'll stop the grid lines. Yeah, this is a nice flower that is in your 11th class. You have so many flowers in that exercise itself. There's only a one chapter that you are seeing there. Of course, one of the problem was solve for this condition, sine 2x minus sine 4x. You have, it is not an exercise problem. It was, they had solved it also. But what are we trying to do here is trying to see when the function, this left hand side becomes 0. Simply try to plot it, just like the way you did in polynomials. It is a root finding problem, nothing else. So let me plot it. Same thing, I'm just plotting it here. Okay, I just did some beautification. This is a nice plot that I get for your problem. And all I need to do check is when the function becomes 0 or when it cuts the x-axis. So you can easily see here at pi by 4, minus pi by 4, pi by 4. minus 3 pi by 4. Those are all, and many more locations are there. Those are the solutions of this problem what I is posed. It's a nice way of imagining the roots of the solution. Of course, you can get more roots by expanding the interval, and you can find the unit cell of it. This can also be mathematically solved. So I'm just solving it as a, like we solve the polynomial equation. It's a trigonometric equation that I'm solving it. The textbook solution was n pi by 4. That's what we see here, pi by 4. And of course, there is one more solution, n pi plus minus pi by 6. That also a portion of it, what you see here. So my request is all your textbook problems, I wish you can visualize it with such, not this, any visualization approaches. So it just comes into your mind so beautifully as you see the problem. That's what I just shown here. So beautiful to see whatever equations what you have in, and all these are from your one chapter of the book. So what are the trigonometric takeaways from us? So polynomials and trigonometries are similar behaving, not the same, similar behaving. One is for a certain kind of problem, other is for a certain other kind of problem. One trigonometry is for cyclic behavior, polynomial is for more linear and local deformations. The root finding, maximization, all those concepts of one can be applied to other or any more things also. So of course, next time you see a flower, like the way when you saw a friend now, you are starting polynomial series in his emotions, or a material also you do that. Likewise, when you see any nice pattern, a cyclic pattern, you can see a trigonometric series in it. You can fit a trigonometric series to it, which you have all read from your class 10 onwards. Then the question comes, if trigonometry is so powerful, why should I do, why can I not avoid polynomial in future? That's why each have their own role, like each of us have our own role in our nature and society, we play a part. Polynomials have a part. Lines, if you try to fit with a trigonometry, you need an infinite series. Likewise, yeah, wave, if you want to do with a polynomial, you need an infinite polynomial series as the bottom equation. So each one have their own part to play in the bigger picture. We'll slightly digress a bit now. Already we have been digressing a lot, so this will be one interesting digression. What I'm having in hand, that this may require a bit of my photo being, I mean my video being shown up also. So what I will do is, I hope one person always keeps his mic on. I hope you are able to see me in camera.
Yes, sir.
Beautiful. Thanks, Bharat. So what I'm going to do is, I'm having a cap of a pen in hand with me. Let me try to create some sound out of it. Oh, sorry, I had to just open it. Yeah, frequency of pen cap. Of course, you know that it's our. I hope you are seeing. I hope it's like a open on one side. Cap is open on one side, closed on other side. So it's like an open pipe. What you must have come across in physics. We will not go into the physics of it. If you see the frequency of first mode, they call it as lambda by 4, where lambda is wavelength, L is the length of your pipe. In this case, our pipe is going to be the pen cap. And after measurement, I show you, convince you, it is close to nearly 40 mm or so. 40 to 45 mm is the length of it. Let me show you. Okay. Let me run through the calculation to find what is the first mode for this pen. Let me find what is first mode for this. First, let me go by calculation. Then we will demonstrate it physically. So pen cap length being 40 mm. I am assuming a wind velocity here as 330 meters per second. Okay, plus or minus few things. It may vary 345 based on temperature. It may vary. And lambda will be first mode is 4 into L. L is my pen cap. Oh, okay. Sorry, I am not. Yeah, output I have suppressed. Let me show you. This is my wavelength, beautiful wavelength. What will be my frequency? These are all straight for you people are far ahead in it. This is the frequency of first mode because I have used lambda by 4. Let me simplify this. Let me further simplify it. Yeah, around 2062. That is the frequency. Let me go and check whether what we calculated. I am showing you a spectrum analyzer, simple spectrum analyzer. While hearing music, you must have seen this. What it shows is merely the frequency components that it is getting. Let me open my camera. Yeah. Now I'm going to blow into the pen. We will see at what. Okay, bottom it is slightly. You are not able to read the frequencies in it. I'll slightly move it up. Yeah. Bottom it shows which frequency component dominates. It keeps changing. I'm just going to blow it up.
Really wonderful, sir.
You can see that around 1800. If you want, you can read in the bottom. It was showing around 1800. Okay, 1875 or plus or minus whatever. So you have calculated frequency and you have captured the frequency. Let us understand why we do this also. If you want to create a different frequency, all you have to change is the length of the pen. Let me take another pen of a different length. That is nothing but our flute. So here, as I start playing, you can see which peaks and how the peak moves. You should have concentrated on your when you see in the screen that is the left hand side. There are other components seen on the. Please see below 1000 hertz. You can see a nice peak, a mountain peak moving in the top. Concentrate on the top portion. If you want, I will try to put a filter so that you don't see some unwanted portions of it. Yeah, that is only a filter what I'm putting. Yes, so you can only see the peaks. Well, it's quite interesting to see. One second. So what you have done is just change the pen length and hence you are playing with the frequency output. So you can create with a set of pens your own nice instrument, but that is not the goal. That is a physicist part. Now being a mathematician, we will see how we can use this understanding. Let me create them. That's the beauty of it because we should be a creator. I will create it. I may take some setup time. Please bear with me. I will assure you that it is worth it. What I'm having in hand is a Bluetooth speaker. So instead of using my laptop speaker, I am going to reroute the output to a Bluetooth speaker. Give me a minute. I think it's getting paired. It's getting slowly paired. Wow, the Bluetooth works. Okay, now going back to our the frequency that we saw can be seen as a sine wave also. If sine wave, I can recreate the sound by simply playing a frequency. So I'm just trying to. You must be seeing a screen here. I will try to zoom that, and I'll try to convince you that this is merely a sine wave by plotting a small frequency to it. Okay. Yes. So I am showing you a simple sine wave. Let me keep increasing the frequency. Let me keep further increasing the frequency. Of course, this may cause a bit of inconvenience playing a single frequency. Please bear with it. What I have done is just played a 400 hertz. Usually, most of our musical systems are tuned to 440 hertz. Let me show you what is the first mode that I played with my flute. That way, let us try to sync this electronic sine wave with our flute wave. So I'll just take the spectrum again. You can see the bottom, what is the frequency it shows as I play. It was showing around 420. You must have seen the bottom. 420 was the value which was showing for the first mode. So let me also mathematically play a sine wave of 420. To convince you that it is showing, I will keep this guy to the side. And let me play the electronic sine wave and see how the spectrum responds. You could have seen once again 420 was the value it played. Flute was showing 420 and the sine wave was showing 420. Now let me join it as it starts playing. Let us see whether I am tuned enough. So this is tuned enough. Whatever I play, it is exactly capturing, which means the natural musical instrument you can capture by a sine series, which means you can create your own instrument by playing with this sine series. That is a part as first learning. We will enjoy it also further. Let me make it slightly out of tune with my flute. Instead of 420 hertz, I will go to 450 hertz. Musicians will not like it at all. They say abaswaram. Let me play that abaswaram. You can note that there was two peaks close to 420. One was the flute frequency, which was at 420, and this electronic which was around 440, causing a beat frequency. That beat frequency, you can usually mathematically you check by minus theta 2 minus theta 1, sine of theta 2 minus theta 1 you usually used to do. That is actually the beat frequency. That frequency is something what musicians will want to avoid in many places. That's why all Carnatic musicians you would have seen, initially they keep tuning it. What they do is they ensure that all their sine series are aligned. They don't want a mismatch in their sine series, whether it is the first mode or any higher mode. One more beauty also, as I was playing, when I played the first 420 hertz, there would have been a peak after some distance to the right hand side. You can see a second peak. At what condition it happens? It happens at 2f, f to f. So around 840 that will happen. That's a second fundamental frequency. The bottom also sometimes shifts between 840 and even 1200. That is the third mode. So F to 2F is usually the one octave, what we physicist terminology of octave and the such thing goes. Now the one more basic question that you can ask. Why should I have only 6 holes in my flute? And why only I should choose? Because between F and 2F, between 420 and 840, there are so many combinations possible. Why should I choose only certain set of combinations? That is where our initial guys like Pythagoras and they found that certain integer ratios somehow makes human feel safe and nice. Presently, there are many models also coming up which says why certain things give music a pleasant sensitive to ears. But those are the basis, mathematical basis that goes into choosing the frequencies of your flute or any other instrument that you may think of. You can also go for a more baser frequency by choosing a bigger pen. So you must be seeing my camera. I was playing with this shorter pen. Now let me play with a still longer pen. You will be getting still lower frequencies. You saw the values were hovering around 320 on that side. So you can keep going to a baser and baser flute, or you can keep going like a pen cap. Pen cap frequency was around 1800 2000. By choosing a shorter length, you can go to still higher frequencies also. So you can play with that. Those are the physics part. Our beauty is we are able to see the sine series of an instrument mapped to an electronic sine series, and both are synced. That way you can create your own mathematical musical instrument. With these thoughts, we'll just go back to here. There is one, though I won't touch much on physics, there is a common misconception that the waves are what is that, a transverse wave, but for a wind instrument, the waves are primarily a longitudinal wave. Longitudinal wave is slightly hard to imagine. As a mathematician, it should be a straightforward activity. Just a hint for you to imagine and understand a wind instrument, how a longitudinal wave will exist. The animation shows, which is courtesy of Mr. Daniel, whose website I have shared at the end. So this is the question that I just posed. Sarigama Padanisa, why do we have only 7? Why not we have more? So that yes, music is something people always keep experimenting with. Some Western system use 12. They call it as equitemperamental scale and so on. So as a mathematician, you can always play with your own frequency range, your own frequency segmentation, create your own frequency instrument. So next time you see a trigonometric series, not only you see a flower or nice cyclic pattern, but you can also hear it. That's the beauty of you can all your senses can get triggered by the trigonometric series. With one small experiment, I will maybe go to the first topic. Once again, you may, I'm just going to play with my camera. We saw it is a one-dimensional, just like in polynomials, we played with 2-dimension to create surfaces. With vibration also, in flute, we created a one-dimensional waveform, but we exist in a 3-dimensional world. So we should be able to visualize higher dimensional vibration also. Let me show you. Same, I'm taking the Bluetooth speaker. I'm taking a plate. I am going to play a sine series and see what happens to it. Please give me a minute to set up. I'll close. Oh, sorry, I just missed to also show you how a musical instrument. On the screen, you must be seeing some numbers. These numbers are nothing but the frequency what I got from my flute, 6-volt flute. I just listed here, created an electronic equivalent or a mathematical equivalent of it. These are the functions. Let me show you what it the sound it creates.
Excuse me. Excuse me.
Yeah, please.
Excuse me. It's a very exciting, interesting presentation. Already time has flown like anything. We didn't know that it has taken 2 hours.
Yeah.
But there will be some interaction with the student, isn't it? Because some of them may find their battery problems and things like that. So that is the only urgency. Otherwise, we would like to continue as much as possible.
Can I just show with 2 experiments and close it? Is it okay? I'll take maximum 8 minutes or so. Is it okay?
Okay, that's fine. And let's have some good interaction.
Okay. So I'm very sorry about it. I just didn't keep a track of the time. Oh, even my battery is going low. So this whatever flute frequency what I got from there, I just put the mathematical equivalent. Let me play it. Whatever we captured, this is a simple sine wave played. So that is one thing, and I'll stop with just one experiment. Or I will do one thing. Rather than showing the experiment, I have captured it. So I'll just show you because I thought it will make a bigger impact. Instead, I have the video anticipating such problems. I will rather show the video. The same plate what I just showed. I kept the plate over a Bluetooth speaker and played a sine wave close to the. You can see the pattern that gets formed on it. This is the one of the fundamental mode for the plate. So we are capturing the behavior of the plate when a changing force. Initially in material characterization, we were seeing the behavior when a static force is given. Here, when a dynamic load is given, we are capturing the behavior. I'll show you one more mode of this. This only I want to show you experimentally. One more mode. Sorry. Whatever the particles that you see is nothing but the Suji rava, which was put on the plate over a Bluetooth speaker, and a sine wave was used to excitation. They get, what are the places it gets aligned? They are nothing but the nodes where node displacement happens. Wherever it gets large displacement or oscillation happens, from there the particles move and go to the place where no oscillation happens, and that is how the nice pattern gets formed. So there is nothing but a 2-dimensional form of the same wave, whatever 1-dimensionally we are seeing here. Of course, how it helps. This is the same way many of our components also behave in the rocket. So we do a dynamic analysis to check how each component dynamically behaves and tries to see what are the sign components present in it. If it is worrisome, then we'll try to suppress it. In this case, we don't need a nice high frequency oscillations. We will try to suppress it. That natural frequency, we don't usually stay in the like we avoided some of the inflections in our material behavior. We also avoid inflections or high points in such vibration behavior. That we characterize by such experiments only. This is a dynamic characterization, which is nothing but component of sine and cosine series. So overall takeaways, with just 2 chapters from your book, we understood material behavior, and we even designed to some extent rocket motor case geometry and found the peak pressure. And you guys have nearly got the hang of it, I suppose. Think about what you can achieve with remaining chapters of your book, because we just touched upon just 2 chapters. I want to touch upon more of it, but maybe in a later time we all will have a nice in-person get together where I can demonstrate all these. This is something what I wanted to give you as a food for thought. This is matrix. Matrix is like a poem for a language. Matrix is a poem for a mathematical expression. It is a food matrix in this case. To create whatever you want, a food item, what are the constituents is captured in the middle. These are the coefficients. So you can see this is a 5-dimensional state. Sure, you can appreciate easily food is existing in more than 3-dimensional space. It is not a physical dimension, it is taste dimension. So you can start going to higher dimensions when you close your eye. Eye only stops you from seeing higher dimensions. Matrices are a beautiful way of seeing mathematical objects. We will maybe in future we will have a time on it. Of course, language to math also there are beautiful connections. Languages, we create a lot of words to tell emotions, but words are never sufficient. So we keep borrowing. These are like integers. Emotions are continuous. So language keeps evolving. The mathematics of language is fantastic. So by this, I just acknowledge being a Teacher's Day. There are many gurus in my life. One of this, I just listed Professor Chandran. He even called me yesterday and asked, "What are you doing?" I was telling I was preparing a talk. He said, "You are not fit for a talk. Do you know what is polynomials?" I hope you know what is the condition now. So he keeps me, like Dr. Radhakrishnan mentioned, always craving for knowledge. So please be in the foot of such gurus who can always show you the ignorant points. So you can always keep learning whatever the age you reach. Mr. Narasimham is one more person who took me to a curved space in the geometric domain. Of course, my friend Sri Kumar, who wrote some of the codes that I just showed today. These are some of the softwares they used, Mathematica and Maple. These are all mathematical programming systems. Not programming, as I showed you, we can simply type it as it is. And you can visualize the beautiful equations that you see in your book. Always pen and paper is the best tool because you are undisturbed. But such tools aid you when you require certain repetitive tasks to be. So these are all tools. Unfortunately, these are not very free tools, but I hope your schools can afford it. And I am not going to promote these 2 tools. Similar tools also exist, so that can be thought about. But such tools should be used to visualize what you work on. Premind is one more tool what I use to organize this presentation. It's a mind mapping software that also we'll talk about. I have not properly acknowledged all the Google source images. Maybe by this I'll just acknowledge. And of course, the beautiful angels, you are the people. I told you, you are ever merciful. I hope you are continuing to be so, being patient enough. The right hand side, what I showed is, I was asked to talk on mathematics in space, but I have talked about all around it. And so with this, I just make my stop. Some of the references are here, which I can share with you in a more detailed way. Thank you, and appreciate all the patience. Please take over, sir.
Thank you, Prasanna sir. We are continuously watching an interaction between two intimate friends. One is Mr. Prasanna and another one is pure mathematics. That we are enjoying. And it was a great journey that we all enjoyed. The time was not at all a problem because we are continuously recording and streaming it through the YouTube. Now any student can watch it with taking his own intervals and analyze it and make his own questions, and these things are this possible now. And definitely we take it as a great occasion, and that will be recorded in the history of this US Space Club. And it is proved that you are a genius in mathematics, not in your mechanics and not in your aerospace MS you received from the Premier Institute, Indian Premier Institute, Institute of Science. And we are proud of you, sir, with us, such an enthusiastic person with us. We are ever thankful to you, sir. And again, some of our students are here. The student army is ready to face you with the questions. Mr. Bharat Srijit and Sriram and Varun, and our master and our Abhinand is also there. He is a student of Raman Institute of School of Mathematics, Pondicherry, and his proud youths are here, and we will face a good interaction with you with the questions. Time is not at all a problem, but it is recorded, and it's a great occasion for us. Thank you, sir. And please, Mr. Sriram, please take over this occasion.
Thank you so much, Rajil sir, for inviting me to handle the Q&A session. Am I audible?
Very much, very clear.
Yes.
Okay, sir. Good evening to all the veterans and eminent personalities and dear friends. First of all, I wish a very happy Teachers' Day to all. And I must say our sincere gratitude to the lead speaker, Prasanna sir, for being patient with us and taking the whole session by going through the deep mathematical topics. We all know that sir is from our own pride institution, VSSC, Vikram Sarabhai Space Center. And like I saw an interesting quote that love is like pie.
So
It is natural, it is irrational, and it is very important. And the whole mathematics is like that. We knew over these sessions that. Okay, Abhinandan.
you just check your voice. It is sometimes it is breaking.
So without any long, I like to start the Q&A session